Okay, then for this lecture we start with a little bit of mantle petrology, because that was our ultimate aim. But before that we need to get into how does the mantle look like. You already know that the mantle is ultramafic composition, that's for sure, and that has olivine, orthopyroxene, cladopyroxene, all very magnesium rich. So this we know from our previous studies, but we need to know a little bit more if we want to look at how the whole mantle thing works. So for that, I have for you two figures. This figure, you must understand one thing, that we do not have access, we have access to mantle-derived melts. We have access. Those melts that has been dredged from the ocean floor or from the continental areas. We have some information, petrological and geochemical information from the melts that are brought to the Earth's surface, that erupt on the Earth's surface, and some are thought to come from very, very deep mantle, from almost the mantle core boundary. There are several models that have been proposed over time, and many of these mantle-derived melts are known to come from the mantle core interface. And you know the mantle core interface, which is the Gutenberg discontinuity, that occurs at 2,900 kilometers below. But if you would like to have a sample, or you know the mantle has melted and melts have come up, but if you would like to know what is the residual rock, then you have a little problem. Residual rock means the partially molten rock. Then you have a little bit of problem, because this does not come up to the surface unless they are brought out by xenoliths. Xenoliths that come with the mantle rocks that are erupted on the Earth's surface or intruded onto the Earth's surface and are now presently exposed. So there is a problem. So although we know that many of the mantle rocks come from great depths, but mantle rocks coming from very great depths, that means from the lower mantle, are almost not known. So what we have is a set of geophysical data. We have P-wave velocities, S-wave velocities, from which we can find out the bulk modulus, the Young's modulus, and the density, K mu rho, from P-wave and S-wave velocities. But they give you numbers of densities, numbers of bulk modulus, numbers of rigidity modulus, and you can also have an idea of what is the variations of this based on certain models. So we have some idea about it. But what particular minerals make up that rock to make it have this K value, the bulk modulus, the mu value, the rigidity modulus, and the density value? What are the minerals and what constitutes them so that you arrive at the values at that depth? That is a little more difficult situation. That is comes into more of thought processes rather than having hard evidence, because we do not have we do not have a lot of samples from such great depths. But anyway, over time the science has developed. New techniques have been developed, and people have been trying to study the deep mantle as much deeper they can go. And based on that, I have prepared for you a diagram which essentially is a plot of the density that you derive from the P wave and the S wave velocity densities, and you can see they have a very jagged path. So overall the density increases, but there are major variations as we move along the density. So the density would change if the chemical composition of the rock changes, or even if there is a chemical composition, but there is a phase change. There is a phase change. Say, for example, a denser mineral becomes stabilized. Then also the P wave and the density values will change. So the density of the mantle is both a function of the chemical composition of the mantle as we go down, also the phase transitions that occur in those zones. So that's a bit of little complication, but we overall it is generally agreed that you can see here that as you have the Moho, for example, so this depth is roughly about 40 kilometers of the crust, and the lithosphere is somewhere here below, so must have been about 100 kilometers depth. And then the velocity starts to go, as you go deeper, there is a small inflection in the velocity, where this inflection occurs because of the dampening of the seismic waves at a depth, as you can see, roughly around 200 kilometers. But this could vary. And this dampening of both the P waves and the S waves has been explained by the presence of melts. And this is called the low velocity zone. So melts. But the total amount of melt that explains the P wave velocity and S wave velocities, the densities, the K values, the mu values, it appears that the total percentage of melting is very small. Geophysical methods tell us that the data cannot be tolerated if there is more than 1% melt. Although petrologists and geochemists would tell you, no, there is a little more melt than what you predict. It's not 10 or 20%, but maybe 5 or 6%. So there is a major discord between petrologists, geochemists on one side and geophysicists on the other side. That the geophysicists say, no, we can't tolerate values more than 1% of melting. The petrologists and geochemists say, okay, but we can't explain some of the melts or rocks that we have unless we induce 5 to 6% of melting. Now, these are the zones of uncertainty. As we go down, the density slowly increases. Then there is a rapid change. You can see that the density sharply changes from here to here in a very small depth range. This is called a major discontinuity. It's not a first order discontinuity, but it's a second order discontinuity. It's a major discontinuity that is around 400 kilometers depth, at roughly 400 kilometers depth. So obviously this change in density would definitely be a function either of the change in the composition or on the phase transition, or like in the low velocity zone, the presence of melts. But presence of melts would reduce the velocity. Here the velocity continuously increases in sharp steps. In sharp steps they increase. So there are jarred part of the density variations. This density at around 400 kilometers, this is thought to be a major discontinuity, a major phase transition boundary. Now what is this phase transition boundary? This phase transition boundary involves, as is suggested now, that you have the pyroxene developing a garnet structure. The pyroxene developing a garnet structure. So pyroxene, you must be wondering, how can a pyroxene become a garnet? Now you can see, if you take a mantle garnet, the value is Mg3, say for example, Mg3Al2Si3O12, right? But you can split it up into 3MgSiO3 and Al2O3. You see? MgSiO3 and Al2O3. So, a pyroxene structure, a pyroxene, or more correctly, if I take a magnesium pyroxene with some amount of aluminium, there are a lot of experimental work which says that the pyroxene increasingly accommodates more aluminium, both in the octahedral and in the tetrahedral sites with higher pressures. So if you have a pyroxene like this, that means if you take a pyroxene like this, I don't have the place to write it, So you can have a pyroxene which can read as MgFeAl AlSiO3. So you can have a pyroxene like this, MgFeAl, AlSi, and this you can split into MgFeSiO3 and Al2O3, and this develops a garnet structure. Have you understood? So this transition essentially means that if you have a pyroxene, then it develops a garnet-like structure. It doesn't become garnet. It develops a garnet-like structure, so it behaves similarly garnet. And therefore, and this is one transition that occurs at around 400 kilometer depth. And the other transition is where olivine, the normal olivine that you see, that olivine transformed into a special type of olivine with a more denser olivine with a different structure, and that is called beta olivine. So these are the two transitions that occur at this boundary where the pyroxenes, including clinopyroxene, pyroxenes develop garnet structure. How does it develop? Because pyroxenes, both orthopyroxene and clinopyroxene, take in a lot of aluminium with high pressure, and as it is, then you can split it up into this. You can also split it up into 3CaMgSiO3. You can do that also. So both clinopyroxene and orthopyroxene takes in a lot of aluminium in its crystal structure, and that is changed into a garnet structure, which is a CaFeMg garnet. So the garnet remains high in magnesium and gracula, but it develops a garnet structure, the pyroxene and Al2O3, which is called the corundum molecule of orthopyroxenes. Corundum molecule of pyroxenes. So you have this discontinuity occurs because of a phase transition of pyroxenes, orthopyroxene and clinopyroxene, to give you a garnet structure like this. I hope you remember this part. Both clinopyroxene will accommodate aluminium, and clinopyroxene accommodates aluminium both in the tetrahedral. This is the tetrahedral site, this is the octahedral site, and so they accommodate aluminium, and you can split the pyroxene formula into a normal pyroxene and a corundum molecule, Al2O3. And this combines to give you a garnet structure. And here, olivine becomes a pseudomorph, not a pseudomorph, transits, it's a phase transition to beta olivine. And this transition explains the change in density over this range. Don't quote my value, these are very famous diagrams. So you can look up in the internet, or you may be knowing some of you. But that's a very important thing. The sharp change in density across this discontinuity is because of pyroxene to garnet structure formation and olivine to beta olivine. Now here, above 400 kilometer depth, this is considered to be the general mineralogy of a mantle rock. This is thought to be the general mineralogy of an upper mantle rock. General mineralogy means if you take this combination, this modal amount, and you find out its volume at these pressures, then it roughly gives you a good correspondence with the seismic wave velocity of K, mu, and rho. So there is a general consensus that if you take this, you know what is a pyrolite model, I hope, famously coined by Ringwood. His final pyrolite model includes 3 dunite and 1 tholitic basalt. There are 4 parts in a pyrolite, and that he takes 1 part as tholitic basalts and the 3 part as dunite. So if you mix them up mechanically and crush it, you get a hypothetical mantle composition, which is called a pyrolite model. So if you take a pyrolite model, these days these are called lazulite model, if you take the pyrolite model and assume that this is the mineralogy of that pyrolite model, this sort of explains the densities around this above 400 kilometers, above this major discontinuity, not a first order discontinuity, and major discontinuity. Below this, however, below this 400 kilometers, below this major discontinuity, you don't have pyroxene because they have reverted to garnet. And you don't have olivine, you have beta olivine. So essentially in this part, below this distance, this and this, the dominant mineralogy is beta olivine and garnet. Roughly in this proportion will give you the density variations as shown here. Have you understood? So that is about a little bit about this mantle. So you start with an olivine, orthopyroxene, clinopyroxene, garnet. This assemblage here gives you the velocity density gradients, and then you have a discontinuity which explains the density variations from here to here, a sharp density variation, and then below that you have the mantle which contains 57% beta olivine and about 43% garnet. There is no pyroxene, and there is no pyroxenes here, and olivine has reverted to beta olivine. Again, all this are magnesium. And then once you have this, then you go down more depth, and you see there is an increase, but again you can see there is a sharp change in density here at a depth roughly about 670 kilometers. This is called now the 670 kilometer discontinuity. Right? So we have a density variation here, and this is explained also by certain phase transitions. Now, before we go into phase transitions, below this phase transition, there are several combinations of minerals that have been tried to explain this density variation and the bulk modulus and the rigidity modulus. It appears that the mineralogy contains 29% MgO is periclase. MgO is periclase. 29% periclase. 22% SiO2, but having the structure of stishovite. Not quartz, stishovite. Quartz is not stable at that pressure temperature condition. So you have periclase, you have quartz stishovite, and then you have 24% of MgSiO3 Al2O3 mark here, and now they don't have the garnet structure, but they have the ilmenite structure. What is the structure of ilmenite formula? FeTiO3, isn't it? This is 6 oxygen minus, so this is 4 plus, and this is 2 plus. So that's classic ilmenite structure. But then you can have AlO3, and this is 3 plus, and this is 3 plus. That's the corundum molecule with an ilmenite structure. And you have MgSiO3, again 2 plus and 4 plus. And so also this is a pyroxene, but with an ilmenite-like structure. So that is very important. So all the pyroxenes that you might have, now you have MgSiO3, Al2O3. You see there is no garnet here. There is no garnet. So the garnet breaks down to MgSiO3, Al2O3, but this has an ilmenite-like structure, not the garnet structure. So MgSiO3, Al2O3 becomes garnet-like structure in this zone, and then this garnet breaks down and you have MgSiO3 with an ilmenite structure. Right? And then 23% of this material, CaFeSiO3, but this is a pyroxene with a perovskite structure. Have you understood? Perovskite, the classic perovskite formula is CaTiO3. CaTiO3 is the classic perovskite structure. So you have CaFeSiO3 that has a perovskite-like structure. And then you have a very interesting mineral, 2% NaAl SiO4. This is necessary to explain the mantle, the sodium content, because I don't know, I have to go back then, because when you have clinopyroxene in the structure, you also incorporate a lot of sodium. To account for that sodium, you have 2 NaAl SiO4, and then a formula, this formula, say spinel. Spinel has a formula MgAl2O4 or FeAl2O4, or for example FeCr2O4, MgCr2O4. So these have spinel-like structures, But these structures are not there. They don't have a pinel-like structure. They have a calcium ferrite-like structure. These are very, very complex structures. So you have then from 57% Ag2SiO4 and 43% garnet across this 670 kilometer discontinuity, something, the breakdown products that you get across this discontinuity, and that creates the discontinuity here, is that, say for example, MgSiO3 can Al2O3 current number, like MgSiO3 to SiO3 of garnet breaks down to MgSiO3 Al2O3. The quartz that comes out breaks down as Si2O5, and then you have CaFeSiO3 as perovskite. The sodium goes into a 2 plus NaLSiO4 structure, and a CaMgAl2O4 produces calcium ferrite structure. So this is the transition that occurs. Just 1 second. It is this structure. I will just erase it. You can ask me, where did MgSiO3 come? Here you can see, if you have Mg2SiO4, this you can break down to MgO plus MgSiO3. You see that? This MgO is very close here. And this MgSiO3 is no more a pyroxene but an aluminium but an ilmenite structure. So these are the transitions that are occurring at 670 kilometers depth. Below this, below this temperature, nothing is known almost. Nothing is known. You can see this is the pressure, of course, because this is the density, this is the temperature. So below this depth, you almost get nothing. So recapitulating, we can say that this is the variation of density. So obviously, in these small parts, for example, there are small sets of phase transitions that are occurring, but these are still not yet well documented. So I'm refraining from this. But the important part is the 400 kilometer discontinuity, from where you get pyroxene converts to garnet structure, olivine converts to beta olivine structure, and then you have a major discontinuity at 670 kilometer depth, 670 kilometer depth, where olivine, beta Mg2SiO4 breaks down to MgO, periclase, MgSiO3 with an ilmenite structure. MgSiO3 with an ilmenite structure. And then you can break down your clinopyroxene to a calcium ferrite structure. You can read more about this if you are interested. There are many internet sites where they will explain it to you in a little more detail. But these are the main phase transitions, and this is the mantle mineralogy. Have you understood? So this is the overall understanding of how the mantle is at depth, say about 670, say maybe up till somewhere close to the core of the mantle, or maybe till about 1,000 kilometer depth. So this is what the data says. So essentially we start with a olivine dominated mantle to then beta olivine garnet dominated mantle, and from there below 670 kilometers you have periclase quartz, 24% NgSiO3 ilmenite, 23% perovskite and calcium ferrite. This is the material that occurs below 700 kilometers. To depth we don't know. To depth we don't know. So this is the modern status of what we know about the mantle mineralogy. In our department, for example, there are faculty members who work with high pressure mantle. So if anyone is interested in this, we can talk to them. Now, there's a second diagram I have placed here. Now this diagram you can see here. This is the temperature. Temperature increases this way and the pressure increases this way. It's slightly odd to see, but that is how this was given by the very famous A.E. Greenwood and the student. So, and it still stays, and it's still one of the very good works that are still taught all over the world. Now this depth is about 200 kilometers. You see, this is depth in kilometer. Depth in kilometer. So essentially this diagram is about this part. Have you understood? This diagram up to a depth of 200 kilometers is essentially in a very small part of this diagram. This is, you see, temperature, so this is not directly relatable, but you can see here, these are some of the diagrams that are depth of 200 kilometers. Now you can see, this is much more shallower part of the mantle, much more shallow part of the mantle. And there you see, the two important thing is, this is called the dry solidus of the mantle. This line is called the dry solidus of the mantle. And this red line is called the wet solidus of the mantle. Wet solidus of the mantle. And these two lines here, these two lines, this is the oceanic geotherm. Oceanic geotherm. And this is the Precambrian continental geotherm. Continental geotherm. This is the dry solidus of the mantle. This is the wet solidus of the mantle. This is the oceanic geotherm. This is how the temperature pressure changes under the ocean. And this is how the pressure temperature changes under Precambrian continental geotherms. That means almost what is being said here is the continental geotherm. And this is the oceanic geotherm. And in between that, this is based on the pyrolite model of Ringwood that I talked about before. Pyrolite mantle of the mantle that I talked before, and 3 parts dunite and 1 part is 3 parts dunite, 1 part tholeiitic basalt. Tholeiitic basalt is the dominant basalt of the ocean basins. So if you mix them up and you produce a mantle, which is a pyrolite. Now experiments have shown that this part, I have written plagioclase, there it contains a plagioclase pyrolite. This is a pyroxene pyrolite. It contains both orthopyroxene and clinopyroxene. And this is called the spinel pyrolite. And this is called the garnet pyrolite. So at the low pressure, you can see here, this is the pressure increasing this way. At depths below, at lower depths, at small depths below the mantle, you will have a plagioclase pyrolite. And then there is some sort of a transformation that occurs where plagioclase is taken out and you have both orthopyroxene and clinopyroxene and olivine, and this is the pyrolite. Here you get a small field of spinel pyrolites at depths of about 50 kilometers but slightly higher temperatures than the pyroxene. And at these depths, above 50 kilometers and above, you get what is called the garnet pyrrolite. In this part, garnet is absent. But in this part, garnet is present. And if you take the wet geotherm, this is the wet geotherm, the wet solidus of the granite. So the mantle will melt at dry conditions here, and it will melt at those conditions at the mantle. We'll talk about that a little later. Now, therefore, from this assemblage, now these are very exotic minerals, and lot of data is not available. Partition coefficient data is not available in many of them. I'm sure it will be generated in due course. But what we have is, we have partition data of this. So of all these minerals that are present here, which essentially is plagioclase, orthopyroxene, clinopyroxene, spinel, garnet, and of course hornblende is also another mineral that occurs here, but it's not shown. But it's not shown, especially close to the wet mantle. So you have horn. Now, therefore, if you look at the mantle, not very deep mantle, but maybe 670 kilometers, maybe. We don't know what is the partition coefficient of beta, whether beta Mg2SiO4 partitions the same way as a normal olivine, we don't know. One has to find it out. But what is important to realize is that we are here where the mineralogy of the mantle would vary, but as we understand, as we go deeper pressures, garnet bearing mantle becomes important. We recognize that the pyroxenes change into the garnet structure. This we must remember. And that olivine changes into beta olivine. So we have some control on this range. Till 400 kilometer discontinuity, as I told you, and this about 670 kilometers of discontinuity. This I have told you before. So this discontinuity. So we have talked about this. So this is what it is. So if we are looking and trying to find out mantle melting, if you are in this range, this depth, lot of data is absent. Partition coefficient data is not very clear. They are used, but some of them are used, but it's not a straightforward use of these data. But this is more or less well known because it has been worked on for so many times. People have converged to certain acceptable values also. But if you go to the different laboratories, the partition coefficient values that they take, they're not one and the same. They are not exact values. There are variations in these values. So if I had to look at mantle melting below a depth of 670 kilometers, I need to know the partition coefficient of elements between olivine melt, pyroxene melt, clinopyroxene melt, garnet melt, plagioclase melt, and spinel melt. But spinel field is very small. We, for the moment, ignore the spinel part. So that is what it is now at the moment. I will now give you a small table এই স্যার তুমি আমাকে এই টেবিলটা একটু ডিকটেট করে দিতে নাম্বারগুলো। তুমি এগুলো একটু ভার্টিক্যালি বলতে পারবে? মিডিয়াম থেকে বলো। আমি দাঁড়া। হ্যাঁ রবিডিয়াম ভার্টিক্যালি বলছো তো? হ্যাঁ
রবিডিয়ামের নর্মাল হচ্ছে 0.010, স্ট্রনশিয়াম হচ্ছে 0.014, ল্যান্থেনাম হচ্ছে 0.007, সিডিয়াম হচ্ছে 0.006, নিওডিমিয়াম হচ্ছে 0.006, সামারিয়াম হচ্ছে 0.007, অয়েলপিয়াম হচ্ছে 0.007,
পরপর বলে যাও। ডিসপরশন
0.013, আরবিয়াম হচ্ছে 0.026, ইটারবিয়াম 0.049, ল্যুটেশিয়াম 0.045। এবারে অর্থোপাইরক্সিন 0.022, 0.040, 0.03, 0.02, 0.03, samarium 0.05, 0.05 তারপর আবার 0.15, 0.23, 0.34, 0.4042, Clinopyroxene, rubidium 0.031, strontium 0.06, lanthanum 0.06, lanthanum 0.056, 0.092, 0.23, 0.445, 0.474, 0.582, 0.583, 0.542, 0.506. Garnet 0.042, 0.012, 0.001, 0.007, 0.026, 0.102, 0.243, 1.94, 4.70, 6.167, 6.950. Plagioclase 0.071, 1.830, 0.148, 0.082, 0.055, 0.039, 1.50, 0.023, 0.020, 0.023, 0.019. এবারে আনসাপোল রুবিডিয়াম হচ্ছে 0.29, স্ট্রনশিয়াম নেই, lanthanum 0.544, no, 0.544, cerium 0.843, 1.340, 1.804, 1.557, 2.024, 2.024, 1.740, 1.642, 1.563.
Okay. So let me just separate these two. It's not so good. Let me separate this now. Rubidium and strontium, these are alkali arc elements. This is very different. But here, these are rare earth elements, except for ytterbium. Oh no, ytterbium is also a rare earth element, yes. So all these are rare earth elements. And if you remember what I taught, the ionic radius decreases as we go from lanthanum, which is a light rare earth element, through the middle rare earth element, and then you have the heavy rare earth element. So this is all rare earth elements. The ionic radius decreases from lanthanum to lutetium. Right? We will talk, I have given this to you so that you remember. But first we will concentrate on the rare earths first. It is important to see that there are certain important things. This is very, very important. I hope you remember. I will just give you an introduction and then continue in the next class. The important point in the rare earths is, let me make a blue color for you so that this, except for these values. Now, what are these values? I didn't tell you. Okay. So this is Ki mineral meth. These values are all partition coefficient values. Partition coefficients given of a particular element. Say this is for rubidium along this column. So you can see this value 0.10 is the partition coefficient of rubidium between olivine and meth. Have you understood? This is the partition coefficient value of rubidium between olivine and meth. Remember, your Ki value is equal to Cs by Cl. Remember? Concentration of an element in the solid divided by the concentration of the same element in the liquid. So these are all partition coefficient values. So this one, for example, if we take this one, say this value, 0.056. What is it? It is the partition coefficient of lanthanum between clinopyroxene and net. So these are all partition coefficient values. Right? Now, you just before, this is a different set of elements. I have given it to you because this will come in very handy later on. This one you should remember, neodymium and samarium. This will also become very, very important later on. So I have listed it within this table. But the most important part, if we look at the rare earths, all values are less than 1. All values are less than 1. Only these values for garnet are more than 1. This value for plagioclase is more than 1. And this set of values for hornblende is more than 1. So the ones in the blue, these elements, partition values are greater than 1. And therefore, they are those elements for those. For plagioclase, only europium. And for amphibole, starting from neodymium to lutetium, these values are compatible. Other than that, all values are incompatible. That means, if, say for example, we just talked about the pyrrolite model, say for example, hornblende occurs in very small proportion, hornblende occurs in very small proportion. So if we neglect amphibole at the moment, then you will see this is the dominant majority of the mantle. Dominant majority that constitutes the mantle. You know, we talked of plagioclase pyrrolites, those are to the lower pressure. Then we talked about pyroxene pyrrolites, those are to the slightly higher pressures. Spinel pyrrolite is a very small, I have not listed spinel here. And then you have a huge field of garnet pyrrolites. So essentially, if you are looking, if we neglect amphibole, plagioclase occurs only in the low pressure garnet, low pressure mantle. In fact, that is the lowest pressure, it's stable. But at higher pressures, it's not stable. So if we omit plagioclase also, that means if you omit this, then you can say the dominant elements, olivine, orthopyroxene, clinopyroxene, this if it is there, all values are lower than 1, incompatible elements. So if you melt the mantle, these elements would be enriched in the mantle. Have you understood? And if you have garnet, then garnet has some higher values, but these greater than 1 values are restricted to the heavy rare earth elements. Heavy rare earth elements. Light rare earth elements are still lower than 1. Okay? I think we will stop here. We will continue with the discussion in the next lecture.